这个我们就一定要跟讲他说他全部都10%。
他 presentation 还有那个 project 的 presentation。
Hello everybody, my name is Ethan Gao, and I'm going to present the question 5119.
不是他跟我在另一面，他是粘进去了。
5119 is about a spring mass system and the system to change the equivalent viscous damping. So let's show the spring mass system first. That's the spring mass system model, and that's that's a K and that's the F applied in this mass. So before we start, we should figure out what's the equal and what's the period of this model. So that's the beginning point, and when the wind is going to vibrate or going to that side, so. And until heat reach to the steady state, first way it goes is going this way, and that's we call X. And going back, one more X, and still going to end of the way, one more X, one back. So that's totally is 4X, which means we can write down like that's the energy dissipation, but it simply is the energy loss. I always say energy loss. So it could be 4x times F. So it will be like 4fx. All right. So that's the whole circle for the and one period is a 4-way. So let's see this graph here. This graph is about the actual pattern on here. So there you go, like a sine graph, which is the whole period with the 4 distance or 4 displacement. We're changing this model to the viscous damping model, so we'll write down. Energy is dissipation. And well, here to integrate here, FD dx. That's about the function of the x with the FD with the damper. And before we're doing this step, we should find the forcing frequency of this whole model. So the forcing frequency is omega equal to 2 times pi times f, which is 2 times pi times pi hertz equal to 10 pi. That's what we call it. Forcing frequency. That's a function of the x, so let's change it. Before we do that step, we'll show you the force about the damper is F equal to say x dot. So equal to Fd times dx dt and dt. So changing it into the function of the dt. So equal to fd x dot times dt. From here we can know ds equal to x dot dt. From here. And this force count, dissipation force. All right. So let's do this x. We know x equal to x sine omega t plus phi. And then we take derivative of this equation, which is x dot equal to omega x 0 cosine t plus phi. And so I said that this is for the whole period, and when there's a period is equal to time t equal to 2 pi divided by omega. So take this into the equation there. D equal to integral 0 to t f d x dot dt, and then fd here, okay, cx dot, so 2 pi divided by omega 0 cx dot times x dot dt equal to 2 pi divided by omega 0 cx dot square dt. Yeah, that's called the viscous damping model, and so let's see out. See. Before dt. And then we'll take the x dot. And omega t plus phi. So that's the final. That's the final. The final function of the viscous damping. So let's these could be rewritten to c omega square x square times pi. Let's say here is like equivalent to viscous damping. And we already got the dissipation energy from the spring system. So let's take this because there's an equivalence for x equal to c omega square times pi. This is our equivalent. Or we take the equivalent to get out. Equal to 4 times x divided by c omega square plus omega square x square times pi equal to 4f. x squared times pi times x. So for the friction we have learned in the physics, which is F equal to mu mg. So the viscous damping, equivalent viscous damping equal to say EQ equal to 4 times mu mg divided by omega squared times pi x. That's the final equation. Final equation to find the equivalent viscous damping. And in the future, if we meet this question, we could use the direct fit from here. So this lot of work is just showing you guys where this equation come from and how it works. So take the data. Take into data 4 times 12 20 times 8 divided by omega squared. The forcing frequency we already found here. 10 pi times pi times the x displacement is 10 centimeter with 0.1 meter. Totally is equal to 15.9 Newton per meter second. So that's the final answer, and that's the equivalent viscous damping.